Okay, good morning. So today we'll finish the discussion of project 1 in which you're going to design symmetric airfoils. I've already posted the project 1 on Moodle, so this will be due next Sunday, so a little more than a week from today. So today is what, lecture 20. So we started talking about project 1 in the last class. So you're designing two airfoils, one for 30 meters per second speed, another for 60. You have to design a fairing around this antenna, just similar to homework 3. And you have to minimize D prime, drag per unit span, for the first airfoil at 30 meters per second at 2 angles of attack, and for the second airfoil at 60 meters per second at 2 angles of attack again. Right, and just to keep track of how well you're doing and just to have some kind of number to maximize, I've defined a figure of merit. So this is a figure of merit that combines two airfoils at 2 speeds, each one at 2 angles of attack. So it's not really a figure of merit for an airfoil, it's more of for your own sake to keep sort of improving some design objective. So let's talk about a possible design process. So firstly, you should get started soon. Have you all installed MFoil yet? If you haven't, you should. Just, it's like with any new code, it's going to take time, and everything from just installing it might cause problems, and then starting to use it and figuring out how to do something. Everything will take a little bit of time, right? Maybe it will work seamlessly, but when does things like that ever happen? Because we are following this project after doing homework 3, I want to make one note here. So this is project 1. So the note is, unlike in homework 1, sorry, not homework 1, homework 3. So do not scale T over C max of the profile So in homework 3, you had some given airfoil to you, and you were scaling the T over C to create, long chord airfoils, small chord airfoils. Here it's a little different. Here you get control over T over C inside profile itself, and that's the way I'd like you to control T over C. So once you take an airfoil from profile, don't rescale the thickness in Xfoil. Okay, so the final airfoils that you submit, the thickness should be what is designed in profile. It shouldn't have been rescaled in Xfoil. And the reason for that is I would like you to think in terms of alpha stars and how alpha stars control velocity gradients and all that. You do all that and you take it to Xfoil and rescale the T over C max, then that connection is lost. Okay, so just use the airfoil as per what you get in profile, and use it in Xfoil. So some of this will get clearer. Let's go through a possible design process. So there is no one way to do this, but this is one maybe set of steps. So maybe you can call this a design iteration loop. Okay, so basically first thing, let's say choose a T over C max, and let's say 12%, which means 0.02, 0.12. So once you choose this, this will decide the pharyng's physical chord. So chord will be 0.025 meters divided by T over C max. This you probably have figured out from homework 3 by now. That will determine the Reynolds number. Right, so now you can go to profile. So in the Newt line, you can set the thickness to chord ratio. In this case, in this example, we have decided on 0.12, so you put 0.12 there. Then run profile. And make sure the Newton iterations converge. And I'll show you what to look for this. Okay, so let's say you've made some modifications to the alpha star and you've arrived at this airfoil and you like it. So if you like this airfoil, save it. Save meaning what gets saved is M foil inside the mfoil work directory, the profile.in will get copied to whatever you save it as. So save it as something like this. So you inside mfoil/runs/ maybe you have a folder called project1, and in that maybe this is your attempt number 25 or something. This is an example name. Right, so this is up to you. You can do the bookkeeping however you want. For example, you could say attempt underscore 12 underscore 25, the 12 being the thickness, so that when you look at the file name, you'll know the thickness, something like that. So you're saving the profile.in. That means you can go back to that airfoil anytime, and you can make some more modifications if you feel like it. But you should also copy the coordinate file so that you can run xfoil on it and you can get the CD, right? You can get CD and the D prime, and you can put it into the figure of merit formula. So on top of this saving, you have to copy airfoil coordinates . So this could be something like copy. So the coordinates are in mfoil/work, and they're in the file called profile.xy. So immediately after you run profile, this file is created. It's got the coordinates. So you copy it to something like whatever folder you have. I'm just going to give some example as maybe this is the folder xfoil_runs project1, and this can be something like attempt 25.xy or .dat or something like that. Right, this is your coordinate file. Now with this coordinate file you can run xfoil. On this attempt 25.xy using unit card. Automatically it will be unit card and the Reynolds number from what we got in the step number 3. So in the previous page we calculated Reynolds number. And once you do that, you can get D prime, which is drag per unit span. And this D prime is just CD from xfoil times half rho V squared C. Right, so CD is from the xfoil run, which will be shown on screen. So you can get drag per unit span for alpha equals 0 degrees and alpha equals 2 degrees. So you'll have to get for two angles of attack, right? So each case you will get a CD from the xfoil run, which is shown on screen. And chord is from step 2. So in the previous page we calculated chord based on the thickness to chord, maximum thickness to chord ratio. So you get the chord, you get the CD from the xfoil run, and you can get D prime. So you have to do this for alpha equals 0, alpha equals 2, and that is for one airfoil, right? That is for one, that's for the airfoil that you're doing. Let's say it's 30 meters per second or 60 meters per second or whatever. So this is a fairly sort of complicated project in the sense that there are many steps to it. So it's very open-ended, and just like in a real industry kind of project, it's time bound, right? You do the best you can within the time available, and it may leave you feeling unsatisfied at the end, especially if you just start late and you work on it only for 2 days, and it's like, oh, I wish I had 3 more days, I could have done better. But that's how almost all design projects are. Anytime you design an airplane, people always know at the end of it, like, now I know what all the mistakes I made. Next time I do this, I'll know what to fix, right? It's kind of like that. So that's the nature of design. But anyway, so you have about a week and a half. At least get some of these things checked out and running properly. That way, when you actually sit and work on it, you've gone past all those steps of installing the code and you kind of figure out how to work with it. Okay, we're going to talk more about MFoil and Profoil. Any questions so far? Okay. Okay, so let's go to MFoil and so I have my MATLAB window open. I'm going to start up MFoil. Yeah. So let's see, let's go to demo 3, which I think we were using this in the last, towards the end of whatever we were doing with MFoil. So we're still going to look at the symmetric airfoil. The demo 3, and I'll open up the file here. This should be inside profoil.in. So I don't know, I'll reload it, I guess. Okay. So this is the airfoil we were playing around with towards the end of last class. And this is the Newton line I'm talking about for thickness, right? We want to set a thickness of 12% or 0.12, and we use this Newton iteration to do it. So one of the things you need to do when you change the thickness is you have to make sure the Newton iteration has converged and the thickness is actually what you want. So let's say I want to make this, let's make it a pretty thick airfoil, 18%, just for illustration purposes. Okay, so I'm going to save this and run Profoil. You can see that thickness has increased. The white dashed line is 12% thick, and the new airfoil is green. We wanted 18% thickness. Not quite sure if that is 18 or not, right? You have to make sure. It's become thicker, but can we be sure it's 18% thick? So one way to do that is to go to the MATLAB window where the Profoil screen output will be there. And there is a line in the statistics that says thick max is 18%, right? So you know this is actually 18%. And These are the Newton iterations. So we'll talk more about Newton iteration in a few minutes. But basically, these are the residuals, and residuals should be pretty small, like 0.000 something. And these are the steps in the Newton iteration. These should also be pretty small, 0.00 something. Like if this is 1 or 0.5 or something, that means the iteration hasn't converged. And usually when that happens, the thickness won't be what you want, or some other specifications. We haven't talked about anything else, but other specifications may not be satisfied. So because we are using this thickness in the fairing design, you have to make sure that you're getting what you asked for. And usually thickness will converge pretty easily. There are some other things later on when you use certain things, they may not converge if you don't give it sufficient amount of iterations, but this should work. Okay, so this is the resulting airfoil geometry and velocity distributions. Again, we are still using a 4-segment airfoil for demonstration. In the actual project, you'll use more number of segments. So, like I said early on, the segment endpoints aren't used to do any kind of splining or anything like that. So just because you use more and more segments is not always good. 4 is the minimum, and that's usually not enough. But don't go overboard and use 100 or something like that. It's just way too many. So something like maybe 8 to 20, that's good, but you don't need to use more. Is not necessarily always better. It just makes things a lot complicated. I'm going to give a template. I'm going to give an example airfoil, and I'll show you what it looks like. I think I put it on Moodle. If not, I have to put it now. So Camembert. Yeah, I think this is the airfoil I give you. So this has got 22 segments. You could just use this itself. And when you have large number of segments like this, you normally don't go and change alpha star for each one by hand. You use the alpha star distribution window that we'll talk about soon. So you can graphically edit some alpha stars. Okay. Okay, so let's now talk about, suppose you want to add a segment. So let's stick with this 18% thick airfoil for now, and I'll save this. Let's save this while we are here. Save file as, I think it's in symmetric. I'll call this demo 4. And let's see how we can insert a segment. Okay, so what is happening is, okay, let me run profile once more. It will clean it up. So now you can see that, for example, at 2 degrees alpha, right? I think we did 0, 2, 4, 6. Those are the alpha values. So yeah, the alpha values at which it's making the plots are 0, 2, 4, 6. So this is 0, 2, 4, 6 on the upper surface and 2, 4, 6 on the lower surface. Okay, so let's take 2 degrees. On the upper surface you have nice favorable velocity gradient up to this point, and then suddenly it's becoming fairly adverse. So at a Reynolds number of say 1 million or something, or even less, 500,000, what will happen is you'll have a lot of laminar flow, good healthy laminar flow that comes till here, and at this point the laminar flow will encounter this big adverse pressure gradient, and it will have a separation bubble, maybe some kind of separation bubble probably, and the bubble will close, but it will have drag due to separation bubble. So maybe one thing to do here may be to soften this favorable to adverse joint, that gradient, right? So one way to do that is to add some segments. We can add some maybe a couple of segments here, and then change the alpha star so that it's a little bit rounded. So I haven't done this in this particular example, so I'm going to just see what happens, try to do it now. Okay, so let me try to do that and walk you through it. Sometimes it won't work because it will take much more time than I have in a class. And also, it takes a little bit of attention, so it's hard to do it as a demo when I'm sort of unpracticed demo, when I'm also talking and doing all those sort of things. Anyway, we'll see. So I'm going to insert 2 segments before the first one. So this is the first segment endpoint, right? I'm actually going to put the first one here, second one here, and make this the third one. Okay, so let me copy this. Just to make it easy, I'm going to create some blank lines so that I can see what I'm doing. So this is 14, right? So these will have to be less. So I'll call this 12.5, 12.5 and 10.5. Will that work? Maybe not. I'll make it 14, 13.5 and 12.5. Okay, and I'll make this, so I don't want this to be too adverse, so I'm going to make the alpha stars, let me make it gradually from 4, I'll start decreasing. No, yeah, let me make it 3 and 2 and see what happens. 3 and 2, then remove these blank lines. I'm saving it, and if I run it, what will happen? It's going to give me an error, but let's this is the sort of thing that will happen to you, so let me actually go through it and tell you how it works, or how to sort of try to debug when you see errors like this. See, it gave me an error. And the errors are cryptic, unfortunately. It'll say index exceeds matrix dimensions, error in blah, 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 error in this, something here. Maybe, yeah, this might give you a clue. It'll give, I think it'll give me a clue. I don't know if it'll give you a clue. But really what you have to do is, unfortunately, so this is a symmetric airfoil, right? So this is actually segment 1, 2, 3, and 4. Fourth segment is the leading edge segment. But here we have said leading edge segment is 2. So you have to make that 4. And I think after that it should work. So that means the point is, anytime you insert a segment on the upper surface, you have to go and change the ILE line. So let's see, we are doing more M-foil demo. We talked about so you have to scroll up and see the FNT And then anytime you add segments to the upper surface, make sure to update the ILE. So this is what happened, right? This is a symmetric airfoil, and this is true even for cambered airfoil. So earlier we had a 4-segment airfoil. So 1, 2, 3, and 4, and we inserted 2 segments here, right? So we wanted to make it something like this. This became 3, and I created 2 segments here, 1, 2, and so this becomes 4. This is 5, 6, 7, and 8. Right? Symmetric airfoil, you're going to give only half the input. You give the upper surface, the lower surface is automatically calculated. But ILE here is 2. Here ILE is 4. If you insert these segments and keep ILE as 2, the profile will get really confused. And in fact, I think even before you go to profile, MFoil catches it and gives an error message. But it's still, I mean, maybe some things can be improved. It can be made more understandable. But the reason is sometimes, there are other things that can happen. And so it's a little hard to create these error messages. Anyway, so now I've made ILE as 4. And hopefully it'll run now. Let's see. So it actually ran. And you can see this is the old airfoil. The old airfoil is in white. It's segment number 1, 2, 3, 4. Now I've inserted these 2 segments, right? So this is now 1, 2, and this is 3. What was 1 has become 3, and this is 4. And then in the velocity distribution, earlier you had favorable gradient at alpha equals 2 or something. Well, it's changed a little bit now. Yeah, I think that's correct. Alpha equals 2, it was favorable gradient, and then became suddenly adverse. Now you've got 2 more segments. I mean, really the problem hasn't gone away because it's become favorable to a longer distance, and then there's sudden adverse. So what you have to do is somehow make these things more adverse, right? So make segments 2 and 3, is that correct? So 1, 2, and 3. So 2 and 3 you have to make more adverse, and you can do that in the file. You can go and say, this is segment 2, and segment 3. You can go and make these more adverse. What do you have to, this is upper surface. The alpha stars are 3 and 4. What do you have to do to the alpha stars to make them adverse? Increase, do you say increase? Decrease? Others? Do you have to increase or decrease? Increase. Right, I think you have to increase the alpha star. When you increase the alpha star, the angle at which you will get flat velocity goes up. No, you have to decrease. You have to decrease the alpha stars. Where are those rules we wrote down in the last class? I think, was it in the last class that we wrote it down? No, it was in the class before that. Yeah, the rule is on the upper surface, increasing the alpha star will make the gradient more favorable. Decreasing it will make it more adverse. Okay, just go back and refer to it. And so we have to decrease the alpha stars. So I'm going to decrease it to, let's decrease it by 1 degree and see what happens. Sometimes the change will be very small and you have to decrease it by more than that. So let me make it 2 and 3. Well, before we do that, before we do that, let me save this as a demo. Save file. I'll call this demo 5. Now I'll decrease the alpha stars by 1 degree each, maybe 2 and 3. And I can decrease this one too. Then it'll be in somewhat progressive order. The first segment alpha star doesn't always matter a whole lot because the alpha star rule doesn't apply there. Anyway, I've changed it, I've saved it, and I'm going to run profile. Well, it's not changed by whole amount. It's not changed by big amount. So I can zoom in here and see it has started to become more adverse. So over here, for example, it's becoming more favorable, slightly more adverse, but not much, and then suddenly it's becoming really adverse. So you can go and fiddle with these numbers, right? The other way to do it is you can edit this alpha star distribution. So this is a plot of alpha star on the vertical axis with phi on the horizontal axis. This is the isolated airfoil alpha star distribution window. So it's usually here, right? So it's usually at the bottom right-hand corner of the screen. And what we've got is, if I zoom in, this point is the phi alpha star versus phi for the first endpoint. The first endpoint was, for this file, is 12.5, right? So let's move this here so you can see it. So this is 12.5 alpha star of 1. So there are 2 points here, right? Two things. One is the circle, this is the triangle. The circle is what you input into the profile input file, like here. So 12.5 and 1. So this is 12.5 and 1. So a couple of things to note here. The phi is actually plotted in a reversed fashion. So phi doesn't increase towards the right. That's because on the upper surface, phi increases towards the leading edge, right? So I've purposely written this interface so that on the upper surface, phi will be plotted in the reverse. So you can always think of this as the leading edge, this as the trailing edge, just like how we draw the airfoil. So this is the first segment, second segment, third segment, and then you go towards the leading edge. So this is 12.5, 1. But then after the Newton iteration is run, the alpha star is changed on the upper surface, right? So the converged Newton iteration alpha star is here. And you can go see that in profile.dmp. So remember, profile.dmp has the converged distribution. And if you go there, you can see the first segment has got 0.41. And that's what this is. This is 0.41. So we set up that Newton iteration to say change alpha stars so that you get a thickness of 18%. And it went and did this. And this is the second segment, third segment. So like that, all the circles are the inputs, the triangles, upward triangles are the converged distributions. Now, anytime you make changes, you're making changes to the input, right? So what we want to do is we want to make this more adverse. So this is the first segment, second segment, and third segment. We want to make all of these really adverse. And one way to do that is to use the cursor edit. And this will start becoming much more useful when you have a lot of segments, like 21 segments. Then you can actually draw some distributions and see how it works. But even here, let's see how to do that. So what I'm looking for is, do I have, yeah, I think somewhere I have an explanation of how this works. Okay, we'll kind of write all this down as well. But when you want to do cursor edit, so normally if you click on the plot, it'll zoom, right? So you can draw a rectangle and then double click, it'll come back to the original zoom. You can single click and it'll keep zooming in. And if you right click, you can zoom out, or double click and it'll go back. But these mouse inputs will change if you start doing cursor edit. So let's zoom in first. I'm going to zoom in like this. It'll keep aspect ratio. So even though you zoom in to this rectangle, it'll do the aspect ratio. So aspect ratio is the same, and that way you can always think of slopes without worrying about whether you're skewing the figure or something. Okay, now I'm going to do cursor edit, and it'll change to this cursor. Now you can actually go and draw some distribution, and it'll then interpolate on the curve that you have drawn at these phi locations, and it'll take that as the alpha star. So it's really complicated to explain, maybe easier to show. Okay, what we want to do is change the input distribution, right? So that's the green line on top with the circles. So let's say I want a distribution like this. I want it to be really adverse. That's something like that. But then I want to draw a curve. So let me say I want it to be something like this. So I'm doing left clicks right now. I can go and insert a point anywhere. And then once I do right click, it'll show me how the interpolated curve looks. So I'm going to do right click, and it'll say, hey, if you want that curve, this is how the input file will look. The input file, we have not changed alpha star of 4, but we have changed alpha star of 3, 2, and 1 to something like this. And if you like it, you can save alpha star edits to file. That means it'll go and write these things to profile.in. If you don't like it, what will happen if you don't like it? I think the safest thing will be to not click this button, run profile, and then it'll come back to where it was. Okay, so let's save alpha star edits to file. Now it's actually written this to file. Okay, so we can go now and load profile.in. Put this back here, profile.in. And it's actually changed the file, right? It's actually added some more stuff. It not only changed these numbers, it actually went and put the lower surface also. And this is for a reason. Even though it's a symmetric airfoil, it actually did all the mirroring and wrote the lower surface. And it actually added these two columns, right? This column and this column. And it put this ILE marker. Well, those are there again for a reason, but for now, let's ignore all those additions, but just see that these things have got changed, right? I think we changed alpha star for segment 1, 2, and 3, and it's become like this instead of whatever it was earlier. Okay, so suppose I like this, I can go and run profile. Now I can see what happens. So it's finished running. I'm going to the statistics. The airfoil is 18%. Now let's go and see the velocity distribution. It's become a little more adverse, right? The earlier one is white. Now the green one is this. That means I have to make a really big change to make it even more nice and smooth. And you can keep going, right? So the way to think about in this plot is, if you move any point upward, it will make it more favorable. If you move it lower, downward, you're decreasing alpha star, you're making it more adverse. So we want these segments to be more adverse, so you pull them down. And okay, let me do cursor edit. Click on cursor edit, and I'm going to draw something like really adverse. And you can say, wow, that looks really wrong. How can alpha star be -10? it kind of doesn't matter. You want a certain velocity gradient and you do what you want to achieve it. So let's say I keep it like this. So I do right click. I guess my last point was here, and then outside the curve you draw, it'll go and pick whatever was there earlier. Does it make sense? So I can go and say cursor edit again and do something like this. And then right click, now it's got a curve. I say, let's save it to alpha star. I don't even have to look at the file. I can go and run profile, and this is the input, this is a converged. Let's look at what it's done to the velocity gradient. Now you can see it's become more, from favorable, it's got one segment of adverse, and then it's kind of rounded it off a little bit, but maybe we don't want this to be so adverse. So segment number 3 can be more favorable. So I can go to the alpha star window, and no, this one. So this is 1, 2, 3. 3 is too adverse. I can make a cursor edit to say I want it to be somewhere here. So I'm drawing the cursor edit only for segment 3, right? It'll interpolate on the curve that I draw. It'll interpolate any segments that are inside, move those segments, everything else it'll leave untouched. So I'm going to keep this here and this here. See, I've drawn only this much. This is just, I want to change this point, right? And I do right click and it's made it like this. Save it to file, run profile. And I mean, this looks a little jagged, but that's not really too much of a concern. What you have to think about is velocity distribution. Now you can see the velocity distribution it's more rounded, right? So it's favorable, little bit adverse, more adverse, and then it's got that. And you can keep going a little bit more. If you want, you can insert one more segment here and make this even more rounded. In the end, you don't know how this is any better. Is this any better than the first airfoil we started with? You don't know. You have to run the two of them in Xfoil, and chances are this will be better. Other thing you can do is you can make this, the two segments that we have added, they're fairly small. You can make them bigger by enlarging this area. You can change the phi values and make them bigger. So in project 2, when you do the cambered airfoil, you'll actually be adding segments like this. This is called a transition ramp. And we'll talk more about this. This is called a transition ramp because it's intended to be a ramp that transitions from favorable to adverse, and instead of having a sharp joint, you have a little smooth curve, just like a highway ramp. You go from a local road to a highway, you have a ramp, right, where you smoothly increase velocity. Like that, this is from a favorable gradient, you can go to an adverse gradient with a nice ramp. And depending on the Reynolds number, this may have to be large or small, and there are lots of considerations here. And a lot of that comes only by experience. Anyway, I'm going to call this, I'm going to save this as the next airfoil. So what did I call the earlier one was demo 5. Now this is demo 6. Save. And now if you want to actually see the difference between, was it demo 4 that we saved this morning, the first one? So in profile.in, I can actually go on, I can insert demo 4, which, let's open that. Oh no. Yeah, open, mfoil, runs, symmetric, all files. Today's airfoil was, today's the 26th, right? Demo 4 was what we started off in the morning with. Yeah, the 18% thick, the first 18% thick was demo 4. So let's click that, and I can actually copy all this. And you see all this star, star, star line at the end, that's the end of the file. So after that, profile won't read anything. So I can actually copy it into profile.in. I mean, I'm kind of doing a shortcut. Maybe I shouldn't do this. It'll confuse you, but I've already started it. So I pasted demo4 on top of profile.in, right? So what happens is it'll run all these things, and when it comes to star, it'll go and it'll stop. Profile will stop, so it won't read the new airfoil here. Okay, so let me run this. And then, so this is where we started off. And then let me delete it now and run it again. So now it will be the new profile. What's the new airfoil called? No, the new airfoil is demo 6. So now we are back to demo 6, and now let's run profile again. And now you can see the white line is demo 4. The green is demo 6, and you can see how much you have changed it. It took maybe 3 or 4 trials, but you've actually been able to make a nice smooth, comparatively it's so much smoother. The white comes, for example, at alpha equals 2, there's a sharp jump. Now alpha equals 2 has this rounded curve to it. Yes?
So if we want to know how exactly the airfoil we designed is good, we have to run the X-foil to get it track.
Correct. So that's the only way to do this. I'm feeling tempted to say, let's go and look how the X-foil looks. I'll leave it up to you. I can put all these demos on Moodle, but you can go run these and take this airfoil and this airfoil and run it in X-foil. And I suspect the demo 6, right? Demo 6 will be much better than demo 4. The white is demo 4, green is demo 6. And you know, that would be so hard to think about with just looking at airfoil geometry. I mean, maybe you can, with some experience, you can say this airfoil is not going to be so good, this will be better. But I think velocity distributions is a more natural step towards how the airfoil is going to perform. Well, what the heck, let's go run this in X-foil. If I get caught up and it takes too much time, I'll abort. But so right now the latest one is demo 6, right? I'm going to call, I'm just going to do, what's this? Yeah, I'm going to work inside the profile work in the mfoil work directory. So I think copy cp, right? COPY profile.xy. I'll copy to demo6.xy. Now, oh, I wish I had. Okay, here is demo 4. I'll copy this and I'll do all that stuff again at the top. Save it. I'll run profile again. Now it's demo 4 is the latest profile run. Now I'll say copy that to demo 4. So I've got 2 airfoils. I'm going to see if I can quickly run Xfoil. Go to command prompt, go to downloads /mfoil. Maybe capital mfoil. What is the directory? No. dir. Oh, where is this? pwd. Why is, oh, not documents. Okay. Downloads mfoil work. I'll use Reynolds number of 1 million as an example. We'll run Xfoil. Oh gosh, what is the Xfoil directory? I mean, all my path and all that is not set up here, so it's a pain. I think it is c:users /ag /downloads /xfoil /xfoil. Okay. Okay, so I'm going to run xfoil, load demo4 first, demo4 dot, what did I save it as? XY. Okay, demo4 dot XY. We'll call this demo4. I'll distribute 200 points, so PPAR N 200, hopper, whisk, Reynolds number 1,000,000, and I'm going to run just one angle of attack, so alpha 0. Did it run? Yeah, I think it converged. You can see there is some sort of an indication of a laminar separation bubble. This is not a definite indication. If you go to VPLO, CF, you'll get, I'm pretty sure, yeah, there's a laminar separation bubble because CF has gone below 0. And we have the CD. So the CD is 0.00790. So let me write that down. So I'm going to write this. Reynolds number of 1,000,000, alpha equals 0 degrees, CD is 0.00790. Now we'll do demo 6, right? I don't know how it's going to be. I'm building up all this, doing all this drama, and it might be worse. It'll be really bad then. Okay, quit. Let's run xfoil again. Load demo6.xy. We'll call this demo 6. PPAR, the usual stuff, N200, hopper, whisk, Reynolds number 1,000,000, 1E6, alpha 0. Okay, let's look at this first. There is still a laminar separation bubble. Maybe it's a little smaller. Okay, so this, now we will do VPLO. I'm not looking at CD yet. There is a laminar separation bubble. It hasn't gone away. Now let's look at CD. CD is 0.00734. Oh gosh, thank goodness. No. So CD is 0.007 what? 34. So it's gone down. So we know this is the correct trend. I'm actually pretty excited about this. Let's go and make a change. I'm wasting class time. We have 10 minutes, right? 11:15, we have 15 minutes. Okay, 5 more minutes, that's it. After that, I'm going to stop. Let's go back to demo 6 in profile.in. This is where demo 6 is. It's at the bottom. If I delete this stuff. Okay, so this is demo 6. I'll save it and run it so that we have this. So run it twice. So this is demo 6. What I'm going to do, oh, you can't see this, sorry. Okay, I didn't do anything. I just put demo 6 back in profile.in. I ran it a couple of times so that we remove the clutter. What I'm going to do is I'm going to make this transition ramp, right? These 2 segments, I'm going to stretch them out to maybe bring this somewhere here and bring this one somewhere here. Okay, let's see what happens. So the way to do that is hard to do with the alpha star editing window. It's best to do that in the file. So instead of 12.5, I'm going to make it 10.5, 10.5, and let me make this instead of 14, it'll have to be between 14 and 30. So I'll make it 19.5 or something. And then let's put this in between. So this will be 15, something like that. 15. Let's put 15.5. Save this, run it. It's become like this. So it has done what I wanted it to do. It's made it really long, but it's okay. So what's happening is this is segment 1, segment 2, segment 3. Maybe I should make segment 3 a little more favorable and leave segment 2 like that. Right, so I can do that here. I want to make segment 1 is here, segment 2 is here. Oh, okay, this is, yeah. One of the glitches with this is once you zoom in and then run profile, and then that zoomed in plot becomes the default. So I can't zoom out now any more than this. It's okay. This is segment 1, this is segment 2. So I want to make segment 1, wait, what was I doing? This is segment 1, 2, 3. I want to make 3 more favorable and 2 more adverse, right? 1, 2, 3. I want to move this up and I maybe leave this as it is. So cursor edit. Maybe we'll try something like this. Okay, I'm going to right click. It's something like this. Save alpha star, run profile. Something happened. It didn't. If these 2 lines are coincidental, then usually profile has not run or something like that. No, it did run. Okay, maybe it's fine. Let's go look at the other window. Okay, so now we are getting something like this. So earlier it was really adverse from here, so now it is a little bit more adverse, little bit more adverse, and then comes here. Let's call this something and run it in Xfoil and see, and after that I'm going to stop, because this is kind of addictive, you know, you can keep on going. So save, I'll go here, save as demo 7. I've saved it. Now I'll save the coordinate file as demo 7. We'll go run Xfoil. Load demo 7.xy. Reynolds number 1,000,000, alpha 0. I think it's a little smaller. There is a laminar bubble, but because you have started having adverse gradient here, the laminar flow is becoming more and more and more unstable. So when it has a bubble, it quickly becomes turbulent, reattaches. So in fact, you can't even see the bubble in this plot. If you do VPLO, CF, well, there is a bubble. I think it's smaller than before. But what is the CD? CD is actually come down quite a bit. So this is demo 7. Okay. Good. The reputation that I hopefully have been building up is not shattered. Okay, so this is kind of how you do design with profile. It's experience plus intuition plus being able to use the tool to kind of make changes the way you think you want, and then go run Xfoil, see if your intuition is correct. If the intuition is wrong, then you say, oh, maybe that's what I should do, and you go try something else, run Xfoil again and say, now I think I'm in the right direction, and then do more of that. And at some point you'll hit a wall, you know, like whatever change you make, you won't be able to decrease CD. And then at that point you say, you know, that kind of design thinking is done. Maybe I should try something else, or maybe time is out and I'm going to say this is my final attempt and finish it. Okay. So just to sort of summarize, we did a bunch of things, right? So what all did we do? So mfoil demo, we did these things. We inserted segments. We edited alpha star distribution using cursor edit. This is going to take a little while to understand, but basically, let's see, you click on cursor edit. So what the alpha star plot. So on the upper surface, the plot will look like this. So this is phi, this is alpha star. So this is more positive. This alpha star will increase this way, but phi will increase this way, because this is the trailing edge, this is the leading edge, and phi on the upper surface goes from 0 to 30, right? So it will go like this. And maybe you'll have a curve like this with some circles, and you'll have another curve like this with upward triangles. And as always, this is the input and this is the converged. So this is what is in profile.in and this is what is in profile.dmp. And there will be two of these. The green solid line like this will be current airfoil. The white dashed line will be the previous airfoil. So there will be 4 lines. Sometimes they'll all be one behind the other. It all depends on what's happening. Okay, so now if you want to edit the alpha star, you click on I'm going to use red to sort of try to denote editing alpha star. You click on cursor edit. And with cursor edit, you can go draw a line here. And you're really trying to change the input, right? So suppose you want to change the input to something like this. So you can go put a point here, and then you put a point here. And it will draw a straight line between those two. And then you insert another point here. Then it will draw a straight line between these. And then you can put another point here. And then in the end, it'll do this. You can keep on doing that. When you hit right click, it will take everything in between these. It will take every segment endpoint in between the first and the last, and then it will move this to here. It will interpolate, it will keep the phi constant, and it will just move the alpha star of the in-between segment endpoints to that. And if you like it, you do save alpha star to edit, to file, save alpha star edits to file. This will update profile.in. So far we are dealing only with symmetric airfoil, so it's only upper surface curve. When we go to Camebird, you'll have one curve for upper surface, one curve for lower surface, and you can toggle. So we'll do that later. And I think this is 19-4. Okay, so we did this, and then we came up with so starting with the first 18% thick airfoil, which was demo 4. We added a transition ramp. and went to then we enlarged the ramp using by changing phi and got demo 7. Each change decreased the CD. All right, so any questions here? So you should actually go now and get started on project 1. You've got everything you need. One thing I'll show is that I'll give a starting file, which is this one. I'll give this example to, if you want to start with this, you can. Let's pull this into profile and see how it looks. So I'll copy this into profile.in at the very top. And let's go run it. I don't know, this is a 8% thick airfoil. That's what is there in my template I've given you, and it does converge. Okay, and this is how it looks. So this is the airfoil. You can now very quickly change the alpha star distribution. Let's put something that's more convex, for example. I have no idea how this will be, so I'm just going to, why didn't it do it? Okay, something wrong. I think I should, I've got 1 minute. Let's restart this. Let's clear all, close all CLC, mfoil, symmetric example 1. Okay. So let's change this alpha star. I'm going to use cursor edit. Right click. So this is a change. I save it to file, run profile, and then it gets something like this. And we change the velocity distribution a little bit. But because you're keeping 8% thickness, in the end, even if you say move all alpha stars up and make it more favorable, then it'll say that'll become like a 18% thick airfoil, right? Then Newton iteration will bring it down, and it'll become, to make it 8%, and then it'll. So what you did is essentially you change the white dashed line to this green line. That's, even though you made it all up, Newton iteration brought it down. So those kind of things will happen. Okay, so I'll stop with this, and then we can talk more on Tuesday.